Okay, so I will continue with my lecture from yesterday. I should have planned it a little bit more carefully because had I just done a few more slides, it would have been helpful for some of the things that Chitaba was discussing. But anyway, never mind. You'll be hearing it again. Hopefully, it'll reinforce what you just heard. So yeah, so just to sort of very quickly kind of bring us back to what the context is for what I'm going to be talking about. So we're looking at the macaque brain, right? And this, as I showed yesterday, was sort of the partition that we managed to find, and we found that that there appear to be 5 modules, and as I showed, this is not something that is specific to the technique that we used, because when we looked over like the space of all possible partitions, we found that the partition that we observed is very close to like the global optimal, and also the membership of the nodes in the partition seems to be fairly robust with respect to small yeah, changes in this in this space. So yeah, so the point is that what we observed, and also the implications in terms of things like the sensory modalities that we appear to find. For example, the fact that the module 5 appears to be primarily focused on primarily concerned with like the visual stimuli, module 1 with olfactory and so on. So that's something that it appears to be not happening just by chance, right? So yeah, so basically that was what that was the crux of what we're talking about. So now I'll talk about something which is actually what Chitara had just mentioned, and this comes from a paper by Guimara and Amaral, and they use the term functional cartography, right? So cartography is just map creation, right? So we're going to use this approach to kind of create a map of the different functions of brain regions. And these are the two sort of measures that were there in the chart, if you remember. So which Shitabra had shown. And so the first measure is that we're going to identify areas that have significantly more or less connections within their own module. And that's going to be computed using this measure, which is the within module degree Z score, right? So that's essentially very straightforward. You look at so you compute for every node the the total number of links between that node and all other nodes belonging to its own module. Right? So basically, how strongly or to what extent is node I connected to other members in its module? I mean, just because you're a member of its module, or member of a given module, you might not necessarily be very active. You might just be present there, but may not be having a very central role. And that is exactly what this Z score is calculating, right? So you obtain that measure, and then this is just the average of all the other your other neighbors in your module. Basically, what is their total number of what is the measure which you compute, and this is just basically so you're just seeing how much more links do you have with respect to everybody else, right? So you just subtract the mean and divide by the standard deviation. That's all you do, right? The other measure is what's called the participation coefficient. So for that, what you do is what you're trying to do is you're trying to distinguish between these areas in terms of the intermodular connectivity, right? So basically, how likely, so you're within a module, but how likely are you to talk to other modules or to have connections with other modules, right? Like for example, you could have like an area which only has connections within its own module, right? No matter how many connections there are, they could have a lot of connections, have very few connections, but only connects to other areas within its own module, right? So we would say that it has a 0 participation coefficient, right? So it's not participating in, you could say, in communication with other modules, right? Um, so basically the way that it's defined is basically as follows. So you subtract this quantity, which is again, so KIC is the number of links between a node I and any node in some specified module C, right? So the sum is taken over all the modules. Yeah, and K is just its total degree. So regardless of whether you're in one module or another module, it doesn't matter. So that's, you're just doing that. And so I wanted to just mention this. So while the participant coefficient of 0 has a very clear interpretation. It means that you are just completely sort of confined to your own module. You're not communicating with any other module. But a participant coefficient of 1 is a bit paradoxical. Right? So it's like you are only communicating with people of other models, or you're equally, I shouldn't say it, like you're equally likely to communicate with people, with members of any module, right? So typically that's not going to happen in practice. I mean, so you can get very close to participation coefficient of 1 possibly, but yeah, that's like the limiting case, right? So you're more likely to have something that's closer to 0, but so in real networks, so we will take a look now at the macaque network and see, by just using these two measures, and of course we need to know what the partitioning is, and that we've already done. So yeah, so with these two measures, we're now going to just sort of have a chart which tells us what could be a possible function of nodes that would lie in this space. So the participant coefficient is on this axis, and the within module Z score is along this axis, right? So remember, so when this is negative, it means there's less connections to members of your own module than would be expected from than would be expected. And when it's high, it means you have way more connections with your own module than the average. So this classification, as I mentioned, was proposed by Guimara and Amaral, and this was sort of heuristically chosen. Like, so you can see here that there's a bunch of different colors which correspond to different. It sort of sort of demarcates the space into a bunch of different regions, but this was done sort of heuristically. There's no sort of when you could in principle have moved the boundaries around a little bit, but it is saying something important, which is that you see that there's a sort of a dividing line over here which sort of splits the top 3 from the bottom 4. These sort of regions up here are correspond to sort of so nodes that lie in those regions would basically be very strongly connected within their own module, right? And these are what they refer to as hubs, right? So you are essentially sort of you're very active in your community, right? Whereas nodes that were down here, I mean, they're present in the module, but they might not be playing such a significant role, right? So these are just what they call non-hubs, right? And going along this axis, you see that here you have a very low participation coefficient, and remember, as I said, when your participation coefficient is low, it means that you are not really communicating with other modules all that much. And so what these are what they refer to as ultra peripheral non-hubs, right? So these are just completely sort of confined to their module and sort of just not participating at all. Then a little bit higher, you get what are called peripheral. So they mostly stick to their own module, but they might have a bit of communication outside. These are connector hubs, so they do now play an active role in communicating. And now 4 are well, these are kind of outliers. So these are called kinless non-hubs. So it's like they almost like don't really have any preference of connecting to their module versus connecting to other modules, right? And up here you have, as I said, so these are now hubs. So when you have a low participation coefficient, it means that you play a very strong role in your module, and you barely talk to any other module. And these are what's called provincial hubs. So these are kind of like they're very provincial, like, so it's like they stick to themselves. The nodes that lie over here are connector hubs, similar to these guys down here, and R7 are what are called global or kinless hubs. Right? So basically, they play. I mean, they're very strongly connected, and they almost don't have any preference about who they're connected to, which model they connect to. Right? So these are like the, you can say like the key nodes in the whole network. But it's again, in reality, it's very unlikely to have a very high participation coefficient in most real networks. But this is just how it was classified. Anyhow, so that should be, I guess, very straightforward. So this is the kind of classification system that they came up with. And this figure which you just saw. So this is what happens when you, yes, sorry, yeah. Yes. It means that you are less likely, you have less connections with other members of your module than on average, right? Because you're computing it from the Z, from here, from the Z score, right? So basically, so if this minus this is negative, then yeah. So So as you were mentioning, so basically, so these are the locations of the various nodes in this space. They're colored according to the module to which they belong, which we've already talked about earlier, and they're sort of sized. I mean, or should say that the size is scaled with the volume. It's not directly proportional, but it's scaled with the volume, which also I've talked about. You notice one thing over here is you have a whole bunch of nodes right at p equals 0. So what does that mean? I've already told you what the answer is. So what does it mean? So when they're all at 0? Someone says? Sorry, there are? No, it means there's only connections inside the node. Yeah. Yeah. So that's what it means. So these nodes over here are only connected to their own model. They do not communicate at all with any other module, right? So yeah. But putting that aside, you'll notice that you have a fairly sort of uniform spread of nodes across most of the regions except for R4 and R7, which means that you barely have any nodes that have almost no preference about who to connect to. And as I was mentioning earlier, it's rare to have nodes that have a very high participation coefficient in some real networks, at least in brain networks, right? So okay, but having found this, well, what does it tell us? So well, if you can actually look at the distributions of the categories specific to each module. So suppose you look at module 1, 2, 3, 4 and 5 separately, you can see, well, what is the distribution of the nodes of each module with the category, and you notice that there's more or less a similar distribution, at least in terms of the the broad features of the distributions across modules. So you don't have any sort of I mean, for example, you see, that you have a much higher sort of proportion of peripheral nodes and so on. You have a few connector hubs and so on. So this is something. This is a feature that is broadly sort of shared, and also remember. So this network is a leaf node network, right? So what as I mentioned on yesterday, what we've done is that we have sort of discarded those nodes that lie at the upper hierarchical levels because of the potential ambiguity. So we're only focusing on the leaf node network. But if we sort of go back up a few steps and look at the higher regions of the brain, so if you look at like the thalamus, the parietal lobe, and so on, and now look at the distributions of nodes that lie within these regions across the R1 to R7 space, you once again find a very similar distribution. In fact, even here we've got the entire brain. This is all the nodes in the network, and you see that there is the same kind of distribution, right? So essentially, what we're saying is what we seem to find is that there's a sort of a similar like fingerprint of the distributions across the functional categories, right? So this could potentially be some sort of indication of the way that this distribution could indicate some sort of um, uh, signature of the kind of information processing that's required. Maybe you need a certain proportion of these nodes. I mean, that we still don't fully know, but I mean that's just some speculation. There are only two regions which have a slight deviation, which is the striatum and the thalamus. So in these cases, you actually don't have any R5 or R7, or barely any R5 or R7. Remember, R5 and R7 are hubs, so you don't have nodes which are strongly connected to its own module in these two regions, right? So that could indicate some sort of homogeneity in the intermodular connectivity. So they don't have any preference for connecting within the module. So that could be something interesting in terms of the functional roles of these regions, right?
So R4 and R7 are the high participation rate.
4, 5, 6. Well, no, sorry. R4 and R7 are the high participation coefficients. Yeah. So in this network, I think even the C elegans these don't show up at all. We don't find any hubs in the thalamus. Yes. Yes.
So what does this? Yeah. Go ahead.
No, I was asking you that thalamus and stratum both not connected or hubs in this.
Yes. Yes. Yes.
Human brain mostly thalamus, stratum are the hubs.
I mean,
Connected hubs.
well, I mean, so this is a hub. Well, I mean, again, it depends on what sort of what do you mean hub? Like in
Yeah, connected hub by participation coefficient and within module degree. How you have classified as connected hubs? So
oh, it's okay. I see. Right. Okay, I'll have to check. So this is, you're talking about in the case of the human brain.
yeah, in
Okay, I'll have to look at that up. But at least in the macaque brain, we don't see that, right?
So
Yeah.
the question is, unless macaques lost it for some evolutionary pressure in the course of evolution, this more is there a functional relevance to this, or physical correlate to this kind of classification, or it's just a classification based, pattern seeking? So whatever you are coming up with.
Sorry, I missed the first part.
In the thalamus,
Yeah.
you see the R7 regions are almost non-existent.
Yeah, actually, in all of them, there's no R7.
Okay, in thalamus maybe R5,
R5 and R6
Now,
are
is this a common evidence in primates, or is this just macaque specific? Or it could be just a classification, or maybe how you have mapped, how the mapping is done. It's a mapping problem rather than.
No, I don't get what you mean by mapping problem, because essentially this is just telling us that the if we define hubs to be regions that are strongly that have strong connections within. Okay, so firstly, let me just go back a few slides. So remember, I had mentioned over here these things, right? So this is a very loose sort of. Not a very rigorous sort of classification of modules in terms of sensory modality. This is just some observation that we had. We tended to find that there seemed to be some sort of broad correlation between nodes that exist in a certain module and some sensory modality, right? So you can very loosely say that connections within the module are connections with other regions that have us that contribute to that modality. So in this case, suppose we say that you have less such connections. It means that there is within the thalamus you have less connections between regions that correspond to the same sensory modality. I guess that's the point. So they might have a bigger role in connecting to other regions which correspond to which do another task. Right. So again, I don't know enough about the biology of the thalamus, but this is just one speculation.
So lacking this R5, R6, and R7, that means that the thalamus is.
It could be more distributed in terms of what its task is. I mean that could be one way of interpreting
more
it.
distributed, then its participation coefficient would be high. So if thalamus because he's participating in other module in the task or something, then their participation coefficient is also high, right? Because participation coefficient is something like involvement in the other modules.
True, but it could have, let's say, for example, R3. Like it does have a like a fairly high R3 as well, right? It could be in terms of that.
Degree is high.
Sorry.
R3 is the where within module degree is high.
No, R3 is low. Within the module degree is low, and but high participation coefficient. Right? So it could be. So yeah, so that is sorry. Yeah.
Completely unrelated. R4 is somehow absent in all the.
So as I say, a node with a high R4, it implies that it has less connections on average with other members of its own module, and the likelihood of connection within its own module and to other modules is more or less the same, right? So in other words, it's almost like it's barely part of any group of any sort of it doesn't really have a clear role per se. It's not really part of a module, and it's not really having a role in connection. So maybe, I mean, so as I was saying, so maybe such nodes in reality don't really exist, right? Because it would be odd to find a node that doesn't do that at all, right? So I mean, pardon?
Because it's localized with tasks, functions.
Because you're saying talking about a hypothetical node in R4.
No. The absence of nodes in R4 implies localization of tasks.
It doesn't have to be localized. It just means that if you're in R4 or if you're, let's say, close to P equals 1, let's say if you're close to P equals 1, then what that means is that there is barely any difference. So going back to the definition over here, right? So which means that this is close to 0, which means that there's barely any difference in terms of your connections within the module and outside of the module. So you're having you're barely a member of that module. Like, let me put it like that. So again, so this is such a hypothetical node is sort of unlikely to exist. I guess that's the reason.
So,
Yes.
So, for example, you came up with this say dividing the brain in macaque brain into 1,000 boxes, right? 1,000 regions.
Okay. Right.
So, for example, now this is true for 1,000 such divisions of the brain.
Okay.
If you correlate the map. Now, if you divide the brain, say 10,000 regions.
Okay.
If you increase the
you're saying that you're basically saying that this is sort of an arbitrary kind of classification to begin. Okay, fine. I agree with you. Yes.
Because I find it so difficult to comprehend that thalamus, which is basically the relay center for all sensory processing except olfaction, and it has such a rich urbanization with almost every other region, hippocampus, prefrontal cortex, and this reciprocal connections.
Yeah.
And have showing very little participation coefficient or say is R5, R6, and R7.
But this is not participation coefficient. This is high number of connections.
Also, it's.
I think the R3 was. I don't know what the R3 was. R3 was sort of high.
For thalamus, you see, it's a flat line. Say from R4. It's
from R4, right? Yeah. But R3 is. I mean, it's not.
Yeah. And we would expect, even if there is low inside the hub connections, there will be very high outside hub urbanizations. So, like all the regions of the brain, or at least the main processing regions.
Right.
So,
I'm not sure if be some kind of connector hub type of thing. So it could have its internal connection as well as they can relay the information to the other advisor also. I don't know about this macaque brain, but in human brain it's generally something like they relay the information. So they have within module connection is high, also they have the participation coefficient is quite high for this.
Okay, again I'll have to check the human brain. I don't know about.
No, but the participation coefficient is high.
Yeah, it is high. Yeah, it is.
Within module.
Module is very less.
Okay, fine. So moving on. So basically now, if we consider the connections, the connections between nodes of different functional groups, right? So basically, if a node belongs to let's say R1 or to R2, you're looking at the connections from R1 to R2 and so on. How likely are these connections with respect to what you would get for your surrogate networks, right? So in the surrogate networks, we have sort of destroyed all the properties except preserving the degree, and also I mean, so remember in my first lecture I talked about having you can also preserve the modular density. I mean, again, not specifically the module location, but the modular density. So such randomized networks, they have the same macroscopic properties as this network, but of course have lost the fine detail. So these are good to compare with. So suppose we I mean, and of course one can do exactly the same sort of functional classification on those networks as well, and then look and see like how much more likely are we to see links of a given type in this empirical network with respect to the randomized networks, right? And so when we did that, so we can do that, and we can compute the corresponding z-score. So I've only just sort of highlighted those nodes over here, sorry, those links over here which are positive. So with the exception of this one, all of these are statistically significant, right? And taking these, we can sort of essentially come up with like a kind of a rough schematic that kind of tells you what is the flow, the could be the flow of information in this network, right? So we see, for example, that there's a huge number of connections going from R5 to R5, right? In fact, I think that this is the only sort of a functional region that has a lot of connections with itself, which again is not super surprising in a way because it's a provincial hub. But anyway, so that's something that shows up, and then and so but we have a lot of connections, for example, between R6 and R2. So R6 are the connector hubs and R2 are the peripheral nodes. And so yeah, so this is something which could tell us something about the flow of information. But to get a better sense about this, we use something which actually Rostam had briefly mentioned in his talk yesterday, which is sorry, on Monday, which is that we check how to what extent the structure of this network is it helps to facilitate the passage of information, and for that we use random walkers placed at nodes on this network, and look at what is the first passage time that, starting with node I, you reach node J, right? When we do this, we can just do this over, can do like large number of simulations, and we find that if we look at the empirical network and look at the corresponding surrogate networks, the degree preserved network and the degree model preserved network. So these are two surrogate networks. We find that surprisingly, you have a higher, you have lower first passage times for the empirical network, right? Which means that you're actually traveling a lot quicker in the empirical network than you are in the randomized network, which is actually extremely surprising, right? You think that when you randomize it, you're now reducing the path length, and so you're going to be able to have information flow more quickly. But no, in fact, it's the empirical network that along which information can travel quicker. This is not surprising, which is that there's if you just consider the flow of information within a module compared to across modules, of course it's quicker within the module, but even so, the solid line represents the empirical network, and then that is quicker in both cases. And finally, using a slightly different approach, which is using Ising spins at each site on the network, as I forget who spoke. I think you spoke about Ising spins. Yeah. So as that was discussed, we find that, and so along this axis is just the temperature, and this is the time taken to reach an ordered state. We find that the the ordering happens more quickly for the empirical network, right? So this is a very different way of trying to measure the same thing in a way. So in this case, basically what we found is that there's something unique about the structure of the empirical network that is allowing for a more efficient sort of passage of information. And we did this. We looked also at the different functional categories, going from R1 to R6, and saying that starting from R1, what would be the corresponding first passage times, and this is measured in terms of the z-score with respect to so basically for the empirical network with respect to its random ensemble, and we find, so basically when it's plus, it means that it's more likely than random. When it's less likely. So you see that lower values are more likely than random, higher values are less likely than random. So in total, it means that there's a significant shift towards lower values, which is interesting. Yeah. So all of that is consistent. Okay, actually, do I want to say anything more of it? No, actually, so yeah, so basically with regards to this part, I think that was the main point that I wanted to mention, is that there is something which is special about the structure of the empirical network, which is facilitating the flow of information, and we suspect that it has got something to do with the fact that, as I showed in this picture over here, there is you do have things like homophily, R5 homophily. So provincial hubs that are connecting to itself. You have the passage of information from the the connector hubs to the peripheral nodes and so on. So these are the kinds of like fine details which might be sort of important for allowing information to to spread a lot more quickly than it is from a purely random network, right? Yeah. So this is the point that I wanted to make with this. So the last thing that I wanted to talk about is, so thus far we have completely ignored the fact. So there's an elephant in the room, which is that the modules have been sort of just assumed to. I mean, so when we computed them, we just assumed that we have a random network and we found the modules, and then we just proceeded with that, right? But this does not consider the fact that the regions of the brains. I mean, we know where they are. We know that there are some which are closer to others, some that are further away from others, and so then that so these are in fact as I mentioned yesterday, Anand had found like through literature sort of detailed literature survey, like what would be like the the coordinates of the centers of each of these regions, and there are of course different sizes, so these are all approximate, but we know what the physical locations of these are, and so how can we be sure that certain properties such as model organization are not just simply some yes yes
These class categories,
yes
categorizations
yes
are also resolution dependent, right? They will drastically change once you increase resolution.
This is strictly using the Guimara-Amaral classification. I mean that those things we have done that. Yeah, and the modules are, I mean, that we've already discussed. The modules are very confident. That's very robust. This is strictly with regards to the Guimara-Amaral classification. Yeah. Okay. Right. So yeah. So how can we be sure that how can we be sure that these properties are not just simply some consequence of this underlying spatial embedding, right? Maybe it just so happens that just the two nodes are proximal, and so then they have a connection. There's nothing more significant than that. It's just that they are neighbors, or they're close together. They're likely to be connected. Much further away, less likely to be connected. So we're just reading too much into it. I guess that's the point. So how can we be sure we're not reading too much into it? So for this purpose, what we should need to do is we need to to find the models, we define a modularity matrix, right? That's what we talked about. So, but this needs to now be redefined such that the expectation that a pair of nodes are connected is going to incorporate, in some sense, the how far apart the nodes are. So for that, we use this approach that is outlined in this paper over here. But very briefly, all we do is we just add an extra sort of function here in this definition of the modularity matrix, which is what's called the deterrence functions. And the deterrence function, all it does is that for if I and j are separated by a given distance d, all it does is it just gives you the weighted average probability that there is some link between nodes separated by this distance. So in other words, if you find that that you have if two nodes which are separated by this distance, if you consider all nodes separated by a given distance, and you say that, well, if you are separated by this distance, what is the likelihood that you're connected, right? So that is going to increase or decrease this f. And so that in turn is going to increase or decrease this expectation. So that is how it's taking this into account, and so by doing so, we're going to sort of nullify any effect that could be artificially introduced by the as I said, the proximity or otherwise of these nodes. So if you look at this starts to, I mean, so this is without calculating the modularity, which is just the macroscopic features, right? So suppose you look at the distances of all the linked pairs, and you find that you have the link, the probability distribution is sort of skewed towards lower values, which means that you have a lot of distances which are shorter than what would be expected. Suppose you consider all possible pairs of nodes. So this does not include the linked pairs; it includes all pairs of nodes. So this seems to suggest that, well, there seem to be more links between proximal nodes than not, and that already starts to give a bit of a warning sign. Okay, this is a bit of a problem. And so when you look at the probability distribution, the connection probability the connection probability between a pair of nodes separated by d, we see that it has a relationship of which roughly has a slope of -1. So this seems to suggest that there is some role of the spatial layout. However, it turns out that when you incorporate this deterrence function and you recalculate the modules with this, so this alluvial diagram shows you that the modules really haven't changed a lot, right? So for example, like so this green module has barely changed. There's just been a little bit of a split here. The purple module has barely changed. The yellow has barely changed. The red one has split a little bit. The blue one has split a bit. But it's almost like it's fairly robust despite completely sort of introducing so it's trying to nullify the effect of distance, right? There is some effect, but it's barely made a dent, right? So that's very good. So then that tells us that this physical proximity cannot just simply provide a causal explanation for the modular structure. The modular structure is coming about because of something else. It's not just because, okay, you guys are all close together, you just form a module, right? So that's what we wanted to ensure is not happening. There's something else which is causing the modules to be formed, right? And as we sort of were sort of alluding to, maybe that has to do with sensory modalities and so on. So yeah, so basically what we show over here is like, so we just try to sort of put together all this information, the adjacency matrix, the modularity matrix, and the distance matrix. In the case of the adjacency matrix, you can sorry, you can clearly see the sort of block diagonal structure, which is what you would expect, right? But if you look at the corresponding distance matrix, you don't find any sort of real difference like within. So you see these white lines, they sort of demarcate where the modules are for this thing, but you see there's not real difference in terms of the distances within the modules and outside the modules. And so then that's sort of straight away telling you that the distance is not really responsible for, or this does not seem to be correlated, have any correlation with the existence or otherwise of modules, right? So that's good. Okay, and okay, I think I could, yeah. So another thing is that um, uh, suppose we want to sort of compare the similarity between two distinct modular decompositions, right? So this is going to be, so I should just sort of preempt this to say that we wanted to verify to suppose we had tried to introduce some null models which were created to sort of to check what would be the effect of having some distance dependent the existence of links being distance dependent. How would that change the partitioning? So that's the reason why we were doing this. But so anyway, but in order to do that, we need some sort of way to measure how much the partitions are changed. So for that reason, what we do is we use the normalized mutual information, which basically just I mean, this is just the formula for the normalized mutual information, where basically CA and CB are two distinct partitionings of so two distinct modular decompositions corresponding to partitions A and B. So these are, yeah, so basically here you have this one is found MA models, this one is found MB modules, and so on. Anyway, so the details are not super important at the moment, but the point is that it is possible to sort of rigorously sort of use this idea of mutual information to compare like the partitions, to say that suppose I know one partition, how much information do I have about the other partition, right? So that's what it tells me, right? So suppose the two partitions are identical, inorm is 1, maximal dissimilarity is when inorm is 0. That's basically all you need to know going forward, right? So okay, so with that, so as I said, so we want to establish that the model organization is not primarily driven by the physical distance between the areas, and so we generate 3 types of surrogate networks, which is specified by some dependence of the connection probability on distance. So the first case, it's distance independent. So this is essentially like a kind of a random network, right? You have a connection probability which sort of completely ignores how far apart the nodes are. So we just create a random network like that. Another one is where it's distance dependent, right? So so basically we're using the same sort of scaling relationship as we have found for the empirical network. Okay, so this is going to become important because although we have the same scaling relationship, we want to see, okay, to what extent will that match what we found in our empirical network, and we also tried to see what would happen if we have an exponential dependence, right? And in all these cases, we looked at the the mutual information, and we found that, okay, obviously for the case of the distance independent one, you don't find a whole lot of difference. I mean, you have a fairly low mutual information. These are just coming about because of fluctuations. In the case of what's it called, of a Paolo dependence, what we find is that you actually have a very low normalized mutual information, right? Which is actually way lower than what you would find in the empirical. So this is actually what you would find for the empirical case, right? And so this is actually very interesting, right? So essentially all we've done is we said that I'm going to use my original sort of way of finding modules, and I'm going to use my new modified way with the deterrence function and just calculate the mutual information. And when I do that for the empirical network, I'm finding a much higher mutual information, whereas I'm not getting that at all. So basically what's happened, it means that essentially it's sort of like completely destroyed over whatever information I have. Suppose I use my deterrence function, right? And so yeah, so that is interesting. So so then again that tells us that that the distance is not playing as big a role in terms of the emerging structure, right? Yeah. Okay. So it's only 5 minutes. So as you can see over here, so so this is actually a representation of what we just observed. So this is just a characteristic sort of surrogate sort of network that we had obtained for the case of this sort of Paolo dependence. And we find that, as you can see, there's now a huge sort of difference between the two types of modular decompositions that we find. We use the original method, we find 4 modules like this. We use the new sort of method with the, where we explicitly have a deterrence function in there, and we completely destroyed the modules. So now they've all been completely split up and they've gone, so the entire sort of decomposition has completely become scrambled over here, right? So this, of course, as you saw, it did not happen at all in the case of the empirical network. Yeah, okay, so I think the only other point that I just want to mention over here is that if you look at the different sort of surrogate networks, and you focus on the modularity value q, you find that once again the q values found for the regardless of which method you use, for the empirical method, the empirical network, the q values are much higher compared to what you get for the random surrogate networks, although again they have exactly the same kind of degree distribution, so it's very similar, you can see. So sorry, not degree distribution, the connection probability, the probability that links of a certain distance d are connected, it's very similar, but still it's completely sort of different in terms of its modularity, right? Yeah, so again, so for the empirical network it's significantly higher. So again, it is something else. So all of this sort of points to the fact that this figure that I showed you a bit earlier is this one. So these are the kind of fine detailed structures which is what is obviously not present in any of the empirical, in any of the surrogate networks, which is what we feel is could be the reason for a lot of the things that we have just shown you, right? So with that, I think is it not moving? Yeah, okay, so that's it. So basically what some of the key things that I just wanted to sort of recap are, as I was mentioning, the specific spatial specific modular organization of this connectome. Actually, it's not, sorry, this is sort of a mistake. It's not modular organization. It's the specific organization of this connectome. The specific organization of this connectome allows signals to spread very fast, in contrast to the kind of surrogate networks that we've shown you, right? So and we talked about why this can be. It could be because of things like the R5 homophily and the preference of connector hubs to connect to peripheral and so on. So these sort of fine details are what is probably key in terms of making the difference in connectivity. And also, as I was sort of alluding to earlier, the fact that there's sort of a the similar distributions in terms of the functional categories, it could suggest, I mean, it does suggest a sort of a uniformity of design which may embody a general computational logic. Now, I mean, we were just having a sort of a debate over this in the lecture. I mean, how much to read into this? I agree that this is just a speculation, but at least this is based on what we've seen so far. And yes, and also another interesting point is, as I was talking about R5 homophily, interestingly, this is actually seen also in the C ligands as well, as in the paper that Chidapa was just mentioning. So maybe it might be a feature of networks that, so they not only need to sort of convey signals rapidly, but also need to process them. So there's a lot of connections within certain groups which may be necessary for processing prior to it being sort of transmitted to other regions, right? And the other couple of, okay, so just a,
so that's also something that Uri alone, for example, found for his microprocessor circuit analysis, which gives more credence to the fact that maybe it's got something to do with information processing.
Right.
It's R5, R5.
Yeah. And so then you may also be asking, like, okay, so we sort of found a broad link between the different modules and different sensory modalities, but how does that help us? Because we don't yet fully know, I mean, all the functions necessarily of a given region. So how does this help us? Well, it's like if we just consider some examples. For example, like the interparietal sulcus. We find that two of the nodes, like which belong to module 2, So these nodes or these regions, they tend to coordinate motor tasks, and actually motor tasks are, if you remember the slide earlier, is partly what we've identified as the role of module 2. So that's interesting. And similarly, the LIP and VIP areas are involved in visual processing tasks, which is and so on. Sure enough, they belong in module 5. So that's consistent with what we've been finding so far in terms of the functionalities of these modules. So I mean, at least what we think maybe is that, suppose the model to which a given brain area is associated with, it may tell us something about some functions of this area that have not yet been identified. Again, this is just something to think about for the future. And the other part, which is an interesting bit of speculation, which is that the some areas which belong to module 4 are known to have a role in social cognition in primates, and they correspond to actually the Broca's and Wernicke's areas in the human brain, which of course the monkeys do not have that ability. But so it raises an intriguing question as to whether these regions that were there in module 5 might have come from some common evolutionary precursor of these areas, and which were obviously responsible for language in humans. So okay, this is just something that just came out of our study, and it's something that's worth thinking about. So yeah, so with that, I just thought I'll just mention that if you would like to know more about this the macaque brain, this is actually a very nice sort of resource over here, which is called the Scalable Brain Atlas. So they have different sort of atlas. I think this is the rhesus macaque, but they also have others as well. I think they even have the mouse and so on. You can actually go through like all the different areas. You have like different slices, and yeah, so you can have a lot of fun playing around with this website over here. And actually all the details of the different areas are in this book, and the recent macaque brain stereotypic coordinates. So you can check that out. I'm scared to go to the next slide. So thank you.